There is a smudge of light in the night sky that most people walk straight past without ever knowing what it is. On a clear, dark evening in autumn or winter, far from the glow of any town, you can find it for yourself if you know roughly where to look. It sits in a quiet corner of the sky, a faint, pale oval, no brighter than a thumbprint smudged across the dark. It looks like almost nothing at all, a blur, a flaw in your own vision perhaps, the kind of thing you might rub your eyes and expect to disappear. But that soft patch of light does not disappear, and it is not a flaw in anything. It is, in fact, the most distant object that the human eye can see, entirely on its own, with no telescope, no binoculars, nothing but the lenses you were born with. And here is the strange and quietly astonishing part. What you are looking at, when you find that faint oval, is not a star. It is not a cloud of glowing gas drifting somewhere out among the nearby stars. It is an entire other galaxy, a vast, ancient gathering of more than 1 trillion suns, slowly turning in the dark, more than twice the size of the galaxy that holds our own sun and earth and every human being who has ever lived. It is called the Andromeda Galaxy, and it lies around 2.5 million light-years away from where you are sitting right now. The light entering your eye tonight, when you look at it, left that galaxy more than 2 million years ago, long before our species existed, and it has been traveling silently across the emptiness ever since, just to arrive at you in this moment. Tonight we are going to take a long, unhurried journey to that galaxy. We are going to travel from its ancient beginnings, more than 10 billion years in the past, all the way to its distant and final future. We will move slowly outward from our own corner of space, across the vast, almost perfectly empty gulf between galaxies, and arrive at Andromeda's outer edge to explore everything we have learned about it. And along the way, I want to share something with you that is easy to miss when you first glance at that faint smudge of light. For almost all of human history, we had no idea what it was. We believed it was a small, glowing cloud living inside our own galaxy. The slow, careful unraveling of what it truly is became one of the great turning points in human understanding. The moment we realized the universe was almost unimaginably larger than anyone had dared to believe. And by the end of this, you will also understand why that distant galaxy is not staying still. It is coming toward us. What that means, and what will happen when it finally arrives, is one of the most extraordinary stories that the night sky has to tell. If you find these slow journeys through space rewarding, and you enjoy taking the time to truly understand something vast, you might consider subscribing. This is a place for curious minds who like to look up and wonder, and I would be glad to have you along for the journey. So let us begin where every great mystery in astronomy seems to begin, with people standing in the dark, looking up, and trying to make sense of what they saw. Let us start, then, with the faint oval itself, and with the question of what it actually is. Andromeda goes by several different names, and each one carries a small piece of its history. The name we most often use comes from the constellation in which it is found, a region of sky named after Andromeda, a princess from Greek mythology with Phoenician roots, who in the old stories was the wife of the hero Perseus. There is something fitting about that. We named the patch of sky after a figure from an ancient legend, never realizing that the faint blur within it was itself a kind of legend made real, a whole world of stars hidden in plain sight. The galaxy also carries 2 more technical names, drawn from the great catalogues of the sky that astronomers have compiled over the centuries. In one, it is listed as NGC 224. In another, far more famous one, it is the 31st entry, which is why you will so often hear it called by its shorthand Messier 31, or simply M31. We will use that name, Messier 31, more than once tonight so it is worth letting it settle in your mind now. What makes Andromeda so unusual among galaxies is precisely the thing we began with. You can see it with the naked eye. This sounds almost ordinary until you understand how rare it is. The universe is filled with galaxies, countless galaxies, many of them far larger and brighter and more crowded with stars than our own Milky Way. And yet nearly all of them are so impossibly far away that they are far too faint for human eyes to detect. They are out there, in their multitudes, but they are invisible to us without powerful instruments. Andromeda is one of the very few exceptions. It is best seen on dark, moonless nights during the autumn and winter months for those of us in the northern half of the world, away from artificial light. And because it can be seen this way, it was noticed by people long before anyone had the faintest idea that other galaxies even existed. This is where the misunderstanding begins, and it is a misunderstanding that lasted for the better part of 1,000 years. Because they could see it but not understand it, people simply assumed that this faint smudge was a kind of glowing cloud, a so-called nebula, sitting somewhere within the bounds of our own galaxy. They had no framework to imagine anything else. The idea that the soft oval might be a separate galaxy, a colony of stars lying far beyond everything else they knew, was not just unproven. It was, for most of history, literally unthinkable, because as far as anyone knew, our galaxy was everything. It was the whole of the universe. There was nothing outside of it to compare it to. The earliest written record we have of this faint object comes from more than 1,000 years ago, in the year 964, in a book written by the Persian astronomer and philosopher Abd al-Rahman al-Sufi. His work, often called the Book of Fixed Stars, was a careful survey of the night sky, and in it he set down a description of a small, hazy patch of light, what he called a little cloud or a nebulous smear. Think about that for a moment. More than 1,000 years ago, a careful observer looked up into the dark, noticed that one faint blur among the stars was somehow different, somehow soft and spread out, rather than sharp and point-like, and bothered to write it down. He had no telescope. He had no concept of what he was truly seeing. But he saw it, and he recorded it, and that small act of attention reaches all the way across the centuries to us. The light he was looking at then is not the same light we see now. The photons he caught had left Andromeda over 2 million years before his lifetime, and the ones we catch today are different again, a fresh wave from the same distant source. For centuries after al-Sufi, nobody studied this faint cloud in any real detail, simply because there was no way to. The human eye can only do so much. That changed in the early 17th century, with one of the great turning points in all of science, the invention of the telescope. Suddenly, faint and fuzzy objects in the sky that had been mere rumors of light could be examined, magnified, and studied. The German astronomer Simon Marius is generally credited with rediscovering the Andromeda smudge through one of these early telescopes, turning his lens upon it and noting what he saw. Even then, of course, the true nature of the object remained completely hidden. A telescope of that era could make the blur a little larger and a little clearer, but it could not reveal that those soft outlines were in fact the combined glow of hundreds of billions of distant stars, far too faint and far too crowded to be separated by the eye. The faint cloud took another significant step into the historical record in the year 1764. This was when the French astronomer Charles Messier was working on a project that would make his name famous among stargazers forever. Messier was, in a sense, a hunter of comets. Comets appear in the sky as fuzzy, drifting smudges, and Messier was forever scanning the heavens for new ones. The trouble was that the sky is dotted with other fuzzy smudges that are not comets at all, permanent fixtures that never move, and these kept fooling him and wasting his time. So Messier did something wonderfully practical. He began compiling a catalogue of all these annoying, comet-impersonating fuzzy objects, a list of things to ignore, so that he and others would not be tricked by them again. The faint Andromeda cloud became the 31st entry on this list, which is exactly why we call it Messier 31 to this day. There is a gentle irony hidden in that. Messier built his catalogue as a list of distractions, of objects he considered unimportant nuisances, and it turned out to be one of the most treasured maps in all of astronomy, because a great many of those so-called nuisances were, in truth, entire galaxies. Messier had no way of knowing it. He was simply trying to find comets. As telescopes improved through the following century, observers began to notice finer and finer detail in the faint cloud. The astronomer William Herschel, one of the most gifted observers of his age, looked carefully at Messier 31 and noticed something subtle. The very center of the object seemed to have a faint reddish tinge to it, compared with its outer regions, which appeared somewhat different. This was a genuinely sharp observation, the kind that only a patient and skilled eye could make. But it led Herschel to a conclusion that turned out to be spectacularly wrong, and in a way that tells us a great deal about how hard this puzzle truly was. Because he could make out such fine detail in the object, Herschel reasoned that it must be relatively close to us. After all, you can only see the details of something nearby. He concluded that Andromeda must be the very nearest of all the great glowing clouds in the sky, and he estimated its distance to be no more than around 18,000 light-years away. Now, 18,000 light-years is an enormous distance by any human measure. But hold that number in your mind, because it is one of the quiet heartbreaks of this story. The true distance to Andromeda is more than 2.5 million light-years. Herschel's estimate was not merely a little off, it was off by a factor of well over 100. He had placed the object comfortably inside our own galaxy, when in reality it was a separate galaxy sitting at a distance so vast that his estimate did not even begin to approach it. And yet you cannot really fault him. Every instinct, every piece of available evidence, every assumption of his age pointed toward a small, nearby cloud. The truth was simply too large to be believed. The next great clue came in the year 1845, and it came from a man with a genuinely remarkable instrument. William Parsons, an Irish astronomer, had built what was at the time the largest telescope in the world, an enormous device that allowed him to peer at faint objects with unprecedented clarity. Turning this giant instrument towards certain fuzzy patches in the sky, Parsons noticed something no one had ever clearly seen before. Within some of these clouds, there was structure. There were graceful, sweeping curves of light, spiraling inward toward a bright center, like cream stirred slowly into coffee, or like water swirling down a drain. He first picked out this spiral pattern in two other objects in the sky, and then, a few years later, in 1850, he recognized that Andromeda and a number of similar objects all shared this same swirling spiral form. He grouped them together into a new category, which became known as the spiral nebulae. But here is the crucial point. Parsons, for all his brilliance and for all the power of his great telescope, still believed that these spiral objects were simply a particular kind of glowing gaseous cloud, drifting somewhere within our own galaxy. He had discovered the very shape of distant galaxies, the elegant pinwheel structure we now know so well, and he still thought he was looking at clouds of gas close to home. The shape was visible, its meaning was not. Yet not everyone was content with the idea that these were merely clouds. There had long been a few thoughtful minds willing to entertain a far stranger and far grander possibility. The most famous of them lived a century before Parsons. He was not an astronomer at all, but a philosopher, the 18th century thinker Immanuel Kant. Kant proposed an idea so bold that it would take nearly 200 years to confirm. He suggested that these faint spiral clouds might not be clouds at all. They might be entire separate systems of stars, vast congregations of suns, much like the Milky Way itself, but lying at distances so immense that they appeared to us only as faint, soft blurs. He called them island universes. It is a beautiful phrase and a beautiful idea that scattered across the void there might be other great islands of stars, each one a galaxy in its own right, each one perhaps holding its own worlds and its own quiet histories. But in Kant's time, and for long afterward, this idea was simply too much to accept. The prevailing belief was that the Milky Way was the entire universe, complete and self-contained. To accept Kant's island universes, you would have to accept that the universe was vastly, almost incomprehensibly larger than anyone believed, with distances so great that the human mind could barely hold them. The scale was too vast, and so the idea remained a curiosity, an intriguing speculation, rather than something that serious astronomers were prepared to build their understanding upon. The turning point, the moment when the question began to crack open, came in the year 1917. An American astronomer named Heber Curtis was studying Messier 31 when he witnessed something dramatic happening within it. He saw a nova, a sudden flaring of light, where a single point in the galaxy briefly blazed up far brighter than its surroundings before fading away again. A nova is a violent event in the life of a star, a sudden, temporary brilliance, and seeing one inside Andromeda was striking enough on its own. But Curtis did not stop there. He went back through the limited collection of old photographs of the object that astronomers had managed to gather over the previous years, scouring them patiently for any sign of similar events. And he found them. No fewer than 11 other novae had flared up inside Andromeda over the years, far more than anyone would expect to see in any comparable patch of our own galaxy. That alone was a puzzle worth pausing on. Why should this one faint cloud be home to so many of these explosive events, so many more than the rest of the sky? But there was a second, even stranger detail, and it was this detail that began to change everything. All of these novae inside Andromeda, every single one, appeared dramatically fainter than the novae astronomers were used to seeing elsewhere in the heavens. They were dimmer by a factor that corresponds to roughly 10 magnitudes, which in astronomy is an enormous gulf of brightness, a difference of many thousands of times. Now think about what that means. If you know roughly how bright these stellar explosions truly are, and you are seeing them as incredibly faint, there is only one sensible explanation. They must be extraordinarily far away. Distance dims everything. A candle held in your hand and a candle on a distant hilltop are the same candle, but one fills your vision and the other is a tiny pinprick. The novae in Andromeda looked like candles on a hilltop, so impossibly distant that it lay far beyond anything inside our own galaxy. In that moment, Curtis understood. He was not looking at a nebula, not a cloud of gas drifting among nearby stars. He was looking at something far more distant and far more profound, a separate and remote colony of stars, a galaxy in its own right, exactly the kind of island universe that Immanuel Kant had imagined a century and a half earlier. Curtis revived that old idea and gave it fresh life, proposing that Andromeda lay around 500,000 light-years away. By the standards of the time, this was an audacious, almost reckless claim. 500,000 light-years placed Andromeda far outside the Milky Way, in a void of space that most astronomers were simply not ready to believe existed. And indeed, the claim was fiercely disputed. The most prominent voice on the other side belonged to another respected American astronomer, Harlow Shapley. Shapley had done extraordinary and genuinely important work, measuring the size of our own galaxy. Through careful study, he had concluded that the Milky Way was around 300,000 light-years in diameter, a colossal figure, and crucially, Shapley considered this to be the size of the entire universe. To his mind, the Milky Way was not just our galaxy, it was everything there was. And so, naturally, Shapley believed that all of these so-called spiral nebulae, Andromeda included, had to be relatively small objects lying within it. The notion that Andromeda might be a separate galaxy, lying not 500,000, but ultimately millions of light-years away, struck him as wildly implausible. This profound disagreement between Curtis on one side and Shapley on the other came to a head in one of the most celebrated episodes in the history of science. It happened in the year 1920, and it has come to be known simply as the Great Debate. The two astronomers met before a live audience at the Smithsonian, in the National Museum of Natural History, to argue out the very nature of the universe itself. The question on the table was nothing less than this: how big is everything? Is the Milky Way the whole of creation, or is it merely one island among countless others? It is a remarkable thing to imagine two scientists standing before an audience, debating the size of the cosmos, with no certain way for either to prove his case. Shapley made his argument with conviction. The Milky Way, he insisted, was the entire universe, and the spiral objects scattered through the sky were simply nebulae residing within it. He pointed out, quite reasonably, that if these spiral objects truly were separate galaxies, then their distances would have to be staggering, on the order of many millions of light-years. To Shapley, and to many in his audience, this was simply a step too far. The universe could not possibly be that large. It would mean accepting a leap in scale that the human imagination of the time was scarcely equipped to handle. He was not being foolish, he was being cautious, refusing to accept an extraordinary conclusion without extraordinary proof. Curtis, for his part, marshaled the evidence he had gathered. He returned again and again to that strange overabundance of novae inside Andromeda, far more than the rest of the Milky Way could account for, all of them mysteriously faint. He argued that no ordinary nebula, no mere cloud of gas, could possibly explain such a high number of these events, combined with their consistent dimness. The only explanation that made sense was distance, vast distance, and a great population of stars to host them. He pointed, too, at the photographs of Andromeda's spiral arms, where dark lanes threaded through the structure. These dark lanes, he noted, looked remarkably like the opaque clouds of dust that lie within our own galaxy, the same kind of dust that blocks our view towards certain regions of the Milky Way. If Andromeda contained dust lanes just like ours, perhaps it was a structure just like ours, a galaxy of its own, only seen from far away. When the great debate ended, there was no clear winner. Both men had argued well, both had marshaled real evidence, and the fundamental question, the true scale of the universe, remained genuinely open. This is one of the things I find quietly moving about this whole story. Here were two brilliant people, doing their honest best with the tools they had, and the answer simply lay beyond their reach. It would take a few more years, and a different kind of evidence, to finally settle it. The matter would not be resolved by debate or by argument, however skilled. It would be resolved by measurement. That resolution came in 1924, and it came from one of the most famous astronomers who has ever lived, Edwin Hubble. Hubble had access to a magnificent instrument, the Great Hooker Telescope, perched on a mountain in California, which at the time was the most powerful telescope in the world. And Hubble had a method, a beautifully clever method, for measuring the distance to Andromeda directly. To understand it, we need to talk for a moment about a very special kind of star, because this is the key that unlocked the entire universe. Scattered through the heavens are stars known as Cepheid variables. These are stars that do something remarkable. They pulse. They grow brighter and then dimmer, brighter and then dimmer, in a steady, rhythmic cycle, swelling and shrinking like a slow, glowing heartbeat. And here is the wonderful thing that astronomers had discovered. The length of that cycle, how long the star takes to complete one full pulse from bright to dim and back again, is directly tied to how luminous the star truly is. A Cepheid that pulses slowly is genuinely, intrinsically brighter than one that pulses quickly. This relationship is precise and reliable, which means that if you can find one of these pulsing stars and time its rhythm, you can work out exactly how bright it really is, in absolute terms, regardless of how far away it sits. Now consider what that gives you. Imagine you know that a particular light bulb, somewhere in the distance, shines with exactly 100 watts of power. You know its true brightness for certain. Then you look at how bright it actually appears to you from where you stand, faint and small in the distance. By comparing how bright it truly is with how dim it looks, you can calculate precisely how far away it must be. The dimmer it appears compared to its known true brightness, the farther away it has to be. This is the principle. A Cepheid variable is like a light bulb of known wattage, a cosmic standard candle, and the universe is filled with them, scattered through the galaxies like markers waiting to be read. Hubble found Cepheid variables inside Andromeda. He timed their pulsations, worked out their true brightness, compared it with how faint they appeared in his telescope, and calculated the distance. And the answer was overwhelming. Andromeda was not 18,000 light-years away, as Herschel had once guessed. It was not 500,000, as Curtis had boldly proposed. It was more than 1,000,000 light-years away, far beyond any reasonable boundary of the Milky Way. There was no longer any room for doubt. Andromeda could not possibly be a cloud within our galaxy. It was its own galaxy, a separate island universe, exactly as Kant had dreamed and Curtis had argued. The great debate was settled, not by rhetoric, but by the patient timing of pulsing stars. I want you to sit with the consequence of this for a moment, because it is genuinely one of the most profound shifts in the entire history of human thought. If Andromeda was its own galaxy, then so were all the others. Every one of those faint spiral smudges scattered across the sky, the ones Parsons had catalogued, the ones astronomers had assumed were nearby clouds, all of them were separate galaxies, each lying tens of millions of light-years beyond our local neighborhood. In a single stroke, the universe expanded almost beyond comprehension. Just a few years earlier, many serious people believed that the Milky Way was the whole of existence, a single galaxy floating alone in the dark. Now, suddenly, the universe was revealed to be filled with galaxies, thousands of them, then millions, then, as we would later learn, hundreds of billions of them, each one a city of stars, each one as real and as vast as our own. The true, terrifying, magnificent scale of the universe had been laid bare, and it had been laid bare by that one faint smudge of light, the one you can still find tonight with your own eyes, the nearest of the great galaxies, close enough to study, close enough to teach us. Andromeda was the key that opened the door to the modern universe. Without it sitting so conveniently near, visible to the naked eye, bright enough to host stars we could measure, we might have remained convinced for far longer that our galaxy was all there was. In a very real sense, that quiet oval of light is the object that told humanity how small we are and how astonishingly large everything else is. Once we understood that Messier 31 was a galaxy in its own right, our whole picture of the cosmos took an enormous leap forward, and Andromeda became one of the most valuable objects in the entire sky to study. The reason is simple, and it is worth appreciating. We live inside the Milky Way. We are embedded within it, surrounded on all sides by its stars and its dust. like someone standing in the middle of a vast forest, trying to understand the shape of the forest itself. We cannot step outside our own galaxy to see it whole, but Andromeda is right there, close enough to examine in detail, and it is a galaxy remarkably similar to our own. Studying Andromeda is the closest we can come to looking at the Milky Way from the outside. It is like finding a mirror that shows us not quite ourselves, but a near twin, allowing us to understand our own home by examining our neighbor. And so we have studied it relentlessly. By the 1950s, astronomers were making radio maps of Andromeda, listening to it across wavelengths of light far beyond what the human eye can see. Today, the great fleet of space observatories regularly turns its attention to our neighbor. Across the decades, the major space telescopes have surveyed Andromeda in ultraviolet light, in infrared light, and in the energetic glow of X-rays, each kind of light revealing a different layer of the galaxy's nature, a different secret. It is worth slowing down here for a moment to appreciate why this matters, because it changes everything about how we understand a galaxy. Your eyes are wonderful instruments, but they can only perceive a tiny sliver of all the light that exists, the narrow band we call visible light. Beyond the deepest red your eye can see lies infrared, the light of warmth and gentle heat. Beyond the deepest violet lies ultraviolet, and beyond that, the still more energetic X-rays. Each of these kinds of light tells a completely different story about what is happening in a galaxy, and a galaxy seen only in visible light is like a song heard with half the instruments removed. When astronomers look at Andromeda in ultraviolet, the hot, young, newly born stars leap out, blazing in regions where the galaxy is busy making fresh suns. When they look in infrared, they can peer through the dust that blocks ordinary light, mapping the cool clouds of gas and the lanes of material from which stars condense, seeing the galaxy's quiet, slow-burning interior. And when they look in X-rays, the most violent objects of all reveal themselves, the dense corpses of dead stars and the regions where matter is being torn apart and superheated near black holes. By layering all of these views together, astronomers build up a portrait of Andromeda far richer and more complete than any single kind of light could ever provide, a picture of the galaxy as it truly is, in all its hidden detail. It is worth noting that no spacecraft has ever been sent specifically to study Andromeda. There has never been a dedicated mission to our great neighbor, no probe launched on the long, impossible journey toward it. We have simply never needed one. The telescopes we built to study far more distant galaxies billions of light years away, find Andromeda an almost trivially easy target by comparison. For an instrument designed to capture light from the very edge of the observable universe, a galaxy under 3 million light-years away is close, bright, and gloriously detailed. The result is that we possess an extraordinary wealth of images and measurements of Andromeda. We have assembled vast mosaics, painstakingly stitched together, that resolve its individual stars in their countless multitudes. We have mapped its interior, charted its structure, and identified within it a rich population of objects, star clusters, glowing clouds of gas, the dense collapsed cores of dead stars, and black holes. What we find again and again is that Andromeda's contents mirror those of our own galaxy, though often on a grander and more dramatic scale. So let us now do exactly what these images invite us to do. Let us set out on the long road to Andromeda and explore what is truly there. But to appreciate what we find when we arrive, we first need to understand the shape and the scale of the thing we are traveling toward. Andromeda is what astronomers call a barred spiral galaxy, and in this, it closely resembles the Milky Way. Picture, if you can, an enormous, slowly turning pinwheel of stars. Sweeping arms of dust and gas curve outward from the center, the regions where new stars are born in glowing clusters, and running through the very middle, rather than a simple round core, there is an elongated concentration of stars, a dense central bar around which the whole structure pivots. This is the basic architecture of both our galaxy and Andromeda, and the fact that the two share this same form is a strong hint that they followed similar paths through their long lives, growing and changing in similar ways across the ages. Andromeda is thought to have formed around 10 billion years ago, in the early, turbulent epochs of the universe. And it has not had a peaceful existence. Like a great city that has grown over the centuries by absorbing the towns and villages around it, Andromeda has grown by colliding with and consuming other, smaller galaxies, swallowing them whole and weaving their stars into its own. This violent, cannibalistic history has left its marks all over the galaxy, and we will see the evidence of it again and again as our journey continues. One of the clearest signs is in Andromeda's very shape, which is notably stretched and elongated, distorted by the gravitational chaos of these past collisions. Let us put some numbers to its scale, because the scale is where the real wonder lives. The bright, visible part of Andromeda, the part that glows in those famous images, is around 120,000 light-years across. That is comparable to the Milky Way, perhaps a little larger, but Andromeda's true extent is far greater than its visible disk suggests. Beyond the bright pinwheel lies an enormous, sprawling region of scattered stars, flung outward over billions of years by the gravitational tides of those ancient collisions. When you include this faint, extended outer halo of stars, Andromeda stretches across something like 220,000 light-years. That makes it, by a comfortable margin, the largest object in our entire local group of galaxies, dwarfing everything else in our immediate cosmic neighborhood. And the number of stars it holds is almost beyond imagining. Even the most generous estimates for the Milky Way are surpassed by Andromeda, which is thought to be home to more than 1 trillion stars. 1 trillion. Let me try to give that number some weight, because it slides off the mind so easily. If you tried to count to 1 trillion, one number every second, without ever stopping to sleep or eat or rest, it would take you more than 30,000 years. Andromeda holds more than 1 trillion suns, each one potentially with its own family of worlds, each one with its own story of birth and burning and eventual death. And it sits there in the autumn sky, quiet and faint, looking for all the world like a thumbprint of light. As for its distance, astronomers have measured it many times over, using a variety of different methods, and most of these measurements agree on a value of about 2.5 million light-years, around 2.56 million light-years, to be a little more precise. This is the gulf we must now cross in our imagination. Before we set off, though, it helps to know a little about the neighborhood we are leaving, because Andromeda and the Milky Way are not alone out here. They are the two dominant members of a small gathering of galaxies that astronomers call the local group, a loose family of perhaps several dozen galaxies all bound together by gravity, drifting through the wider universe as a single cluster. Most of the members of this family are small, faint dwarf galaxies, modest collections of stars that orbit the two giants. The Milky Way has its own retinue of these little companions, and so, as we have seen, does Andromeda. And then there is the Triangulum galaxy, the third largest, a respectable spiral in its own right. Together, all of these galaxies make up our cosmic home address, the patch of the universe to which we belong. And the two great anchors of this little family, the two heavyweights whose gravity holds much of it together, are Andromeda and the Milky Way, facing one another across 2.5 million light-years of darkness, slowly being drawn together. To travel from one to the other is to cross the entire breadth of our home group, from one of its pillars to the other. So let us begin the journey, and let us begin it by rising up and out of our own galaxy, leaving the familiar behind. The first stage of this enormous journey takes us up and away from the flat plane of the Milky Way. We live within the disk of our galaxy, and looking outward through it is a little like looking through a thick haze, with the light of countless nearby stars and clouds of dust dimming and obscuring our view of what lies beyond. But as we rise above this crowded plain, the haze thins. Less and less starlight stands between us and the deeper universe, and the true scale of everything begins to reveal itself. Once we have passed beyond the outermost stars of the Milky Way and slipped past its faint, ghostly satellite galaxies, the small companions that orbit our galaxy in the dark, we cross a threshold. We enter intergalactic space. I want to pause here because intergalactic space deserves a moment of your full attention. It is, in a very real sense, the emptiest place that exists. In a universe shaped and gathered together by gravity, where matter is pulled into stars and galaxies and great clusters, the spaces between the galaxies are what remains, the vast voids left behind, and they are empty almost beyond comprehension. Let me try to make this real for you with a comparison you can actually feel. The air around you right now, the ordinary air you are breathing as you listen, is dense with matter. In a single cubic meter of it, a volume roughly the size of a large box you could wrap your arms around, there are something like 10 trillion atoms. That is a 10 followed by 25 zeros, a number so large it has no meaning to us except as a kind of overwhelming fullness. Every breath you take draws in an unfathomable swarm of molecules. Now let us travel upward, out beyond the atmosphere, into the space just above the Earth, the region where satellites orbit and astronauts float. Surely that is empty, and yet even there, in what we call the vacuum of near-Earth space, a single cubic meter still holds around 1,000,000 trillion atoms. Far thinner than air, yes, but still teeming by cosmic standards. Now let us go further, out into interstellar space, the great gulfs that lie between the stars within our galaxy. Here, finally, things grow genuinely sparse. A cubic meter of interstellar space contains only around 1,000 atoms. From 10 trillion down to 1,000, an almost unthinkable thinning of matter. But we are not done. We must go further still, out into intergalactic space, the void between the galaxies themselves. And here, we reach a place so empty that a single cubic meter, that box you could wrap your arms around, holds, on average, just 10 atoms. 10. You could sweep your hand through a volume of intergalactic space and disturb fewer atoms than you have fingers. This is the ocean we must cross to reach Andromeda. It is darkness and silence and very nearly perfect nothingness, stretching for millions of light years. And yet, for all that emptiness, it is not entirely nothing. There is, it turns out, something out there in the great gulf, and it is one of the loneliest things in all of existence. Scattered through intergalactic space are stars and even entire planetary systems that have been cast out of their galaxies altogether. During the violent collisions that galaxies undergo, the same kind of collisions that built Andromeda, the immense gravitational forces involved can fling some unfortunate stars and their worlds clean out of the galaxy, hurling them into the void between. These are the most ill-fated objects in the cosmos. Imagine a planet, perhaps not so different from our own, torn from its galaxy and thrown into the intergalactic dark, drifting alone, with no companions and no destination. The conditions on such a world are as cold and as lonely as anything that can exist. Out here, beyond any galaxy, there is no nearby star to provide warmth, no sun to anchor a day, nothing but the faint, distant glimmer of unreachable galaxies on every side. A rogue planet adrift in intergalactic space would freeze, utterly and completely. Its atmosphere, whatever gases it once held, would freeze first, and then the freezing would work its way down, layer by layer, through the crust, through the mantle, all the way to the core, until the entire world was a solid, frozen sphere, dark and silent, falling forever through the emptiest space there is. It is a sobering thought to hold as we make our crossing. Somewhere out in that void, such worlds are drifting right now, frozen monuments to ancient catastrophes, and we will never know their names. We are, by now, about halfway across the gulf, and something subtle begins to change. We start to stray, ever so slightly, into Andromeda's territory, not yet into its glowing fields of stars, not yet anywhere near the bright spiral we can see in photographs. Instead, we enter its outermost reaches, its enormous and almost invisible galactic atmosphere. Just as our own Milky Way is wrapped in a vast, tenuous envelope, so too is Andromeda, surrounded by a diffuse halo of plasma, a thin, hot, electrically charged gas that extends far, far beyond the visible galaxy. This halo is thought to have been blown outward with tremendous force, expelled by the shockwaves and reverberations of Andromeda's many past collisions, the same violent mergers that shaped everything about it. The scale of this halo is genuinely difficult to believe. It reaches outward with a radius of something like 1.3 million light-years. Let that sink in. The distance from us to Andromeda is around 2.5 million light-years. Andromeda's halo extends more than half of the entire way toward us. In a sense, Andromeda and the Milky Way are not as separate as they appear. Our galaxies are reaching toward one another through these immense, invisible halos, their outermost edges very nearly brushing against each other across the dark. When you look up at that faint smudge of light, you are looking at the bright core of something whose true, full extent fills a vast fraction of the space between us. We are already, in the faintest sense, inside its embrace, and it is here, within this great halo, that we begin to encounter Andromeda's family, because Andromeda, like our own galaxy, does not travel through space alone. It is accompanied by a retinue of smaller galaxies, satellites that orbit it in the dark, bound to it by gravity. Andromeda is currently known to host more than 20 of these satellite galaxies, and it almost certainly had many more in its past, companions that it has since drawn in and devoured over the eons, adding their stars to its own. Each of these satellites carries clues about Andromeda's turbulent history, and 3 of them in particular are worth our attention, because they are thought to have played key roles in shaping Andromeda into the skewed, elongated, complicated galaxy we see today. They are known as Messier 32, Messier 1110, and Messier 33, this last one also called the Triangulum Galaxy. Let us visit each in turn, because each tells a different and rather poignant story. Messier 32 appears, in close-up images of Andromeda, as a small, fuzzy blob of golden light, sitting near the great galaxy like a smaller companion drawn close to a parent. It is a dwarf elliptical galaxy, modest in size, only around 6,500 light-years across. And yet, hidden at its heart, there is something startling. Messier 32 is held together by a supermassive black hole, more than 1,000,000 times the mass of our Sun. Now pause on that, because it does not quite make sense at first. That is an extraordinarily massive black hole to find at the center of such a small galaxy, a galaxy that modest should not, by rights, possess such a heavyweight at its core. It is a little like finding the engine of a great ship installed inside a tiny rowing boat. Something does not add up, and the explanation is one of the more haunting stories in our neighbor's history. Astronomers suspect that Messier 32 was not always this small. They think that, long ago, it may have been a far grander galaxy, perhaps its own spiral, or a structure called a lenticular galaxy, larger even than the triangulum galaxy we will visit shortly. It was a galaxy of real substance, with a massive central black hole appropriate to its size. But then it came too close to Andromeda. As the two galaxies approached one another, drifting within touching distance, the immense gravity of mighty Andromeda began to tear at the smaller galaxy, stripping away its outer regions, peeling off its stars and its gas, like wind tearing leaves from a tree. The unfortunate galaxy was simply not large enough to survive the encounter intact. Its outlying stars were absorbed into Andromeda, scattered into the larger galaxy's body, and what remained, when the violence had finished, was only the dense central core, the heart of the galaxy, still bound tightly around that surprisingly massive black hole. So today we see Messier 32 as a small, golden, elliptical blob, populated by aging stars, the surviving remnant of a once greater galaxy that came too close and paid the price. The oversized black hole at its center is the tombstone, the marker of how large it used to be. The second of our three satellites is Messier 110, another elliptical companion of Andromeda, and a somewhat larger one, stretching around 17,000 light-years across. Like Messier 32, this galaxy is thought to have interacted closely with Andromeda in the past, to have felt its great neighbor's pull and paid a price for the encounter. Astronomers have detected, threaded through Andromeda's halo, faint lanes of dust enriched with heavier elements, the metals that stars forge in their cores and scatter when they die. These faint, metal-rich streams are believed to be made up of stars that were stripped away from Messier 110 as it ventured too close, its outer stars combed off by Andromeda's gravity and left as a ghostly trail across the larger galaxy's outskirts. But I want to invite you to do something with Messier 110, something I find genuinely moving to imagine. Picture, just for a moment, that you lived on a world somewhere within Messier 110, orbiting one of its stars. Picture standing on the surface of such a planet at night and looking up. You would not see a faint smudge, the way we see Andromeda. You would see the great galaxy itself, vast and luminous, filling a huge swathe of your sky. From that close, Andromeda's enormous disk, seen nearly edge-on, would stretch across the heavens, a river of light and dust and stars, consuming the night, far larger and brighter than any moon. Now think about what that would have meant for a young civilization, for beings just beginning to look up and wonder, as our own ancestors once did. Think of the myths they would have woven, the religions they might have built, the sense of awe and terror and meaning they would have drawn from that overwhelming presence hanging permanently in their sky. Our own ancestors had only scattered points of light and a faint band across the dark to inspire their stories. Imagine what they would have made of a whole galaxy blazing overhead. It is one of the quiet privileges, and perhaps quiet limitations, of our particular place in the cosmos, that our sky is as modest as it is. The third of these companions is the most significant, and in some ways the most uncertain. It is Messier 33, far better known as the Triangulum galaxy. Triangulum is no minor blob. It is, at present, the third largest member of our entire local group, after Andromeda and the Milky Way themselves. It is a dwarf spiral galaxy, around 60,000 light-years across, holding something like 40 billion stars of its own, a substantial galaxy by any measure. And there is an open question about it that astronomers have not fully settled. We do not actually know for certain whether the Triangulum galaxy is a true satellite of Andromeda, genuinely bound to it and orbiting it, or whether it is simply its own independent galaxy that happens to lie nearby, around 750,000 light-years beyond Andromeda. The two possibilities are quite different in their meaning. What we do know, with confidence, is that Triangulum and Andromeda have interacted in the past. Within the last few billion years, these two galaxies came close enough to feel one another's gravity, to pull at one another and leave their marks. And the evidence strongly suggests they will interact again in the future. Whatever the precise nature of their relationship, the Triangulum galaxy and its 40 billion stars are caught up in the same great gravitational drama as everything else in this corner of space. In the long run, those 40 billion stars face one of two fates. They may be drawn in and absorbed into a new, combined galaxy, woven into something larger, or they may be flung outward, banished from the local group entirely, cast into the intergalactic void to drift alone. Which of these will happen depends on the intricate gravitational choreography still to unfold, a dance whose final steps lie billions of years in the future. We will return to that future before our journey ends, because it is a future that involves us too. And so, at last, after millions of light years of dark and lonely traveling, after crossing the near-perfect emptiness of intergalactic space and drifting in through the vast plasma halo, we begin to approach the galaxy itself. But even now, we are not quite there. Beyond the halo, before we reach the bright spiral we know from photographs, we pass through a denser, extended disk of stars, the scattered population thrown outward by all those ancient collisions, stars flung from their original orbits and left to drift in the galaxy's wide outskirts. And then, finally, we break through into the visible component of Andromeda, the great barred spiral itself, rich with dust and gas and the heavy elements that stars create. In its broad strokes, it looks much like our own Milky Way. But look closer, and you find that Andromeda's spiral structure is more complicated than ours, more tangled and irregular, deformed by billions of years of gravitational wrestling with companions like the Triangulum galaxy and others. Where our galaxy's arms sweep in relatively clean curves, Andromeda's have been pulled and twisted and disrupted, bearing the scars of its violent social life among the other galaxies. In fact, in the late 1990s, a space telescope studying Andromeda in infrared light made a surprising suggestion about the galaxy's structure. The observations hinted that Andromeda might actually be in the process of transforming into something called a ring galaxy. The dust within its body, rather than forming simple spiral arms, appeared instead to be gathered into a series of overlapping rings at various distances from the center, like ripples spreading out across a pond after a stone has been thrown in. And that image is more than just poetic, because a ring structure like this is often exactly what you would expect to see after one galaxy has plunged through another, sending shockwaves rippling outward through the disk. Andromeda's rings may be the frozen echo of an ancient impact, a collision recorded in the very arrangement of its dust. In the years that followed, further observations, this time from another great infrared telescope, refined the picture. They revealed two main spiral arms, reaching out from the central bar and extending beyond those rings. But these arms are not smooth and continuous. They are broken, fractured into something like 7 distinct spiral segments, separated by junctions where hydrogen gas is piled up and compressed. And it is precisely at these junctions, these crowded crossing points where gas is squeezed together, that something beautiful happens. New stars are born. The compression of the gas triggers vigorous star formation, lighting up these regions with the fierce glow of newly kindled suns. Andromeda, for all its great age and all its violent history, is still a place where stars are being made, where new light is constantly coming into being in the crowded corners of its arms. One of these star-forming regions deserves a special mention because it is one of the largest of its kind in the entire local group. It is known by the catalog name NGC 206, and it sits at a boundary where two of Andromeda's southwestern spiral arms meet. NGC 206 is an enormous cloud of gas and young stars, around 4,000 light-years across, a stellar nursery on a truly grand scale. And within it lives a cluster of more than 300 blue supergiant stars, blazing with a fierce, intense light. These are not stars like our Sun. They are giants, with diameters dozens of times that of our Sun, burning hot and blue and brilliant, and burning through their fuel at a furious rate. Blue supergiants live fast and die young, shining with tremendous brightness for only a few million years before exhausting themselves. To find more than 300 of them gathered together in one place is to find a region of the galaxy in the full, brief flower of its youth, a place where the cosmos is busy making new things. If you could stand within NGC 206, the sky around you would blaze with the light of hundreds of these brilliant blue suns, a furnace of creation set against the dark. NGC 206 is far from the only cluster in Andromeda. As we explore the galaxy, we find clusters of stars in great abundance. In particular, Andromeda is home to a remarkable number of what are called globular clusters. A globular cluster is a tightly bound, roughly spherical swarm of stars, often very old, packed densely together and orbiting through the outer regions of a galaxy like a self-contained little city of suns. Our own Milky Way has a respectable collection of them, well over 100, but Andromeda puts us to shame. Astronomers have identified more than 460 globular clusters within it, more than 3 times the number we have found in our own galaxy. It is yet another reminder that, in so many ways, Andromeda is the Milky Way's grander, more populous cousin. Among all these hundreds of clusters, one stands out above the rest, the most massive that we know of in Andromeda. It contains several million luminous stars, an enormous swarm, far more than a typical globular cluster, and these stars span a wide range of ages and a wide range of chemical compositions, some richer in heavy elements than others. And this is curious, because the stars within a true globular cluster usually form together at roughly the same time, out of the same material, so they tend to be similar in age and composition. The great variety found in this particular cluster is a clue that it might not be a true globular cluster at all. Instead, astronomers suspect that it may be the disrupted heart of yet another small galaxy that Andromeda swallowed long ago, much like the story of Messier 32, only on a smaller scale. The picture is much the same. Once upon a time, this may have been its own small galaxy, with its own gravitational anchor at the center. When it came within reach of Andromeda, its outer layers were stripped away and dissolved into the broad fields of stars around it. But the dense core survived, held together by a black hole at its heart, an intermediate-sized black hole of around 20,000 times the mass of our Sun. And so today, those surviving stars cling to that black hole as it sweeps around through Andromeda, the whole assemblage masquerading as an ordinary globular cluster. But it is a disguise. Hidden within is the last remnant of a vanished galaxy, the surviving heart of something that Andromeda consumed in the deep past. Everywhere we look, it seems, our great neighbor wears the trophies of its conquests, the swallowed cores of galaxies that came too close, scattered through its body like relics. When we step back and consider Andromeda's overall population of stars, it lines up well with what we find in the Milky Way. There are old stars and young stars, stars in clusters, and stars wandering alone, glowing nebulae where new suns are forming, the dark remnants of dead stars, and, in all likelihood, worlds, planets. Among more than 1 trillion stars, there must be a great many that resemble our own Sun, and around those sun-like stars, there must be planets, perhaps countless planets capable of supporting the kind of conditions that life on Earth requires. The trouble is, Andromeda is simply too far away for us to see them. We struggle to directly image planets even around the stars of our own galaxy, our immediate neighbors. To pick out individual worlds orbiting individual stars across 2.5 million light-years is, with our current technology, simply impossible. And yet, remarkably, there is a hint, a single tantalizing clue, that we may once have glimpsed the gravitational shadow of a planet in Andromeda. Back in 1999, astronomers detected something called a microlensing event coming from the direction of the galaxy. To understand what this means, you need to know one of the stranger consequences of how gravity works. Gravity, as Einstein showed us, bends the path of light. When light from a distant, bright object passes very close to some massive object on its way to us, the gravity of that intervening mass acts a little like a lens, bending and focusing the light, briefly magnifying and brightening the distant source. This is microlensing. And the lovely thing about it is that even objects far too small and faint to see directly, such as a planet, can reveal their presence by the way their gravity warps the light of something brighter behind them. The event detected in 1999, given the rather technical name PA99N2, was just such a flicker of magnified light. And one possible explanation, a genuinely exciting one, was that the light of a distant red giant star within Andromeda had been briefly warped and brightened by the gravity of a planet passing in front of it, a world estimated to be around 6 times the mass of Jupiter, a true giant of a planet. If that interpretation is correct, then for a brief moment, more than 20 years ago, we caught the faint gravitational fingerprint of a planet orbiting a star in another galaxy entirely, a world 2.5 million light-years away. But there is a melancholy catch. Microlensing events like this happen because of chance alignments, fleeting moments when an intervening object lines up just right with a background star. These alignments are essentially random and unrepeatable. The particular configuration that produced that flicker of light in 1999 will, in all likelihood, never occur again in any timescale that matters to us. We cannot go back and check. We cannot wait for it to happen once more and study it properly. We are left with a single, unrepeatable glimpse, a possible planet seen once and then lost forever to the randomness of the cosmos. But even setting aside that one uncertain glimpse, we can say with real confidence that Andromeda, like the Milky Way, must be home to billions of planets, circling its countless stars. A great many of those will orbit stars much like our Sun, and a great many of those, in turn, will sit at the right distance to allow for worlds not unlike the Earth. Somewhere in that faint oval of light, there are almost certainly oceans, and storms, and continents bathed in the light of alien suns. We will never visit them. We will likely never even know they are there, but the simple weight of the numbers tells us they exist, an entire galaxy's worth of worlds, 2.5 million light-years beyond our reach. Alongside all these living stars, Andromeda also holds its dead ones, and these too we can detect. When we survey the galaxy in X-rays, the high-energy light given off by some of the most extreme objects in the universe, we find a scattering of intense sources. Studying these has led to the discovery of dozens of candidate black holes within Andromeda, the collapsed remains of massive stars that ended their lives and crushed themselves into points of infinite density. We have also found possible neutron stars, another kind of stellar corpse, the impossibly dense cores left behind when a massive star explodes, where the matter of an entire star is compressed into a sphere only a few miles across, so dense that a single thimbleful would weigh as much as a mountain. Andromeda, in truth, is likely crawling with these dead stellar cores, the dark leftovers of generations upon generations of stars that have lived and died over the galaxy's 10 billion years. For every brilliant living sun, there is a graveyard of those that came before. But the most significant black hole in all of Andromeda is, of course, the one that sits at its very center, and the center of Andromeda turns out to be one of its strangest and most fascinating features. When astronomers looked closely at the galactic core, they found something they did not expect. The core is not a single point. It appears to be split into two distinct concentrations of light, what is called a double nucleus. The two regions have been given the rather plain names P1 and P2. The first, P1, is the brighter of the two, but oddly, it does not sit at the true center of the galaxy. It is offset, sitting to one side. The second, P2, is dimmer, but it does lie right at the center, exactly where you would expect the heart of the galaxy to be. For a while, this double nucleus was a genuine puzzle. How could a galaxy have two centers? The explanation that emerged is rather elegant. The dimmer, central concentration, P2, is where the real action is. It contains Andromeda's supermassive black hole, the gravitational engine that anchors the whole galaxy. The brighter, offset concentration, P1, is thought to be not a separate center at all, but rather a dense blanket of bright stars gathered into a kind of elongated ring or disk, orbiting around that central black hole. Because of the way these stars move and bunch up along their orbits, lingering at the far end of their elliptical paths, they create a bright concentration of light that sits off to one side, giving the illusion of a second nucleus. So Andromeda has not two hearts, but one, surrounded by a glowing crowd of stars that only makes it look as though there are two. And the black hole at that true center is a monster. It is estimated to be more than 100 million times the mass of our Sun. To put that in perspective, our own Milky Way also has a supermassive black hole at its core, an object called Sagittarius A star. But ours is comparatively modest, weighing in at around 4 million solar masses. Andromeda's central black hole is more than 20 times more massive than ours. Why such a difference between two otherwise similar galaxies? The answer, once again, comes back to Andromeda's violent history. Every time Andromeda swallowed another galaxy, every collision and merger in its long and turbulent life, it gained not only stars, but also great quantities of gas and matter funneled inward toward its core. And a black hole grows by feeding. Over the eons, Andromeda's central black hole has feasted on far more material than our own galaxy's black hole ever had access to, gorging itself on the gas of consumed galaxies until it swelled into the overwhelming giant we find today, 100 million suns of crushed matter hidden in the fractured heart of the galaxy. So now we have explored Andromeda from its outermost halo to its very core. We have crossed the empty void to reach it, drifted through its plasma atmosphere, met its companion galaxies, wandered through its tangled spiral arms and glowing nurseries, counted its clusters, glimpsed the shadows of its planets, surveyed its dead stars, and stood at last before the monstrous black hole at its center. It is a magnificent place, our great neighbor, grander than our own galaxy in nearly every measure, and it would be easy to think of it as something permanent and distant, a beautiful fixture of the autumn sky that will hang there, faint and unchanging, forever. But that is not the case. Andromeda is not staying where it is, and to understand why, we need to return to something I mentioned at the very beginning, the strange fact that this galaxy is coming toward us, because the journey to Andromeda is, at present, completely impossible for us to make ourselves. Even if we could somehow escape the gravity of the Milky Way, the time it would take to travel even a single light year, with any technology we can presently imagine, would far exceed an entire human lifetime, and we would need to cross more than 2 million of them. We cannot go to Andromeda, but here is the extraordinary thing. We may not need to, because in time, Andromeda is going to come to us. The first clue to this remarkable fact is hidden in plain sight, in the color of the galaxy itself. When you study detailed images of Andromeda, one of the things you might notice is a subtle bluish tinge to its light. Now, you might assume this is simply the natural color of its stars, and in part, the color of stars does play a role. But there is something more going on, something that reveals one of the deepest truths about the galaxy. That bluish quality is, in part, the signature of a phenomenon called blue shift, and to understand it, we need to talk about one of the most useful tricks in all of astronomy, something called the Doppler shift. You have experienced the Doppler shift yourself, many times, even if you never knew its name. Think of standing by the side of a road as an ambulance or a police car races past, its siren wailing. As the vehicle approaches you, the pitch of the siren sounds high, and then, the instant it passes and begins racing away, the pitch suddenly drops, becoming noticeably lower, that familiar falling wail. The siren itself never changed. It produced the same steady tone the whole time. What changed was the motion of the vehicle relative to you. As it approached, the sound waves were bunched up, compressed together, raising their pitch. As it receded, the waves were stretched out, lowering their pitch. That is the Doppler shift, and it applies not only to sound, but to light as well. Light, like sound, travels in waves, and the color of light depends on the length of those waves. When a glowing object moves away from us, its light waves are stretched out, shifted toward the longer wavelengths, toward the red end of the spectrum. We say its light is redshifted, and when an object moves toward us, its light waves are compressed, shifted toward the shorter wavelengths, toward the blue end. Its light is blue shifted. So by carefully measuring the color of the light from a distant galaxy, by examining exactly how its wavelengths have been shifted, astronomers can tell whether that galaxy is moving toward us or away from us, and how fast. It is a beautiful thing that the simple color of light can carry within it the speed and direction of an entire galaxy. Now, here is what makes Andromeda special. The overwhelming majority of galaxies in the universe are redshifted. Their light is stretched toward the red, which tells us they are moving away from us. And the reason for this is profound. The universe itself is expanding. The fabric of space is stretching, carrying galaxies apart from one another, so that nearly everything in the cosmos is receding from nearly everything else, drifting ever farther into the distance as the eons pass. Across the vast scale of the universe, the general motion is one of separation, of things flying apart. Against this near-universal backdrop of redshift, of galaxies fleeing into the distance, Andromeda stands out as a striking exception. Andromeda is blue-shifted. Its light is compressed toward the blue, which means that Andromeda, almost alone among the galaxies, is not retreating from us. It is approaching. It is heading directly toward us, closing the gap at something like 110 kilometers every second. Why should Andromeda defy the great cosmic expansion that pushes nearly everything else apart? The answer comes down to gravity and to proximity. The expansion of the universe is relentless on the largest scales, but it is also gentle, and over short enough distances, the gravity between objects can overcome it. Andromeda, the Milky Way, the Triangulum Galaxy, and the other members of our local group are all close enough to one another that their mutual gravity wins out over the expansion of space. We are gravitationally bound together, a small huddle of galaxies, holding hands against the pull of the expanding universe. And because we are bound, we are not flying apart. We are falling together. Over the coming billions of years, the entire local group will gradually draw inward, the galaxies pulling on one another until they coalesce, merging into a single great object. And the first and most dramatic act in that long process will be the head-on collision of the two giants, Andromeda and the Milky Way. Let me walk you through this slowly, because it is one of the most extraordinary events the future holds, and it unfolds over timescales that dwarf anything in human experience. In the next 2 billion years or so, Andromeda will gradually grow in our night sky. That faint smudge you can barely make out today will, over those immense stretches of time, swell and brighten, creeping up in size until it becomes larger and more prominent than the moon, and brighter than any other object in the night apart from the moon itself. Imagine that. A galaxy, a great spiral of 1 trillion stars, growing visibly in the sky, no longer a faint blur, but a vast, luminous structure dominating the heavens. Picture how this would unfold, for any eyes that might be there to see it, across spans of time so long that they make our entire recorded history seem like a single heartbeat. At first, over millions of years, the faint oval would simply grow a little less faint, a little more defined, until one could begin to make out the structure within it, the bright core, the sweeping arms, the dark lanes of dust threading through. Then, over further millions of years, it would continue to swell, until it was no longer a curiosity to be sought out on dark nights, but an unmistakable presence, a great glowing pinwheel hanging in the sky, larger than anything else up there. The spiral arms would become visible to the naked eye, vast rivers of light arcing across the dark. There would be no single dramatic moment, no sudden arrival. It would be the slowest of approaches, a galaxy drifting closer across 100 million human lifetimes, growing so gradually that no individual generation would notice the change, yet utterly transforming the sky over the long reach of time. Of course, there will be no humans as we know them to witness it, and the Earth itself may be very different, but the spectacle would be breathtaking beyond words. As we move further forward, to around 3 billion years from now, Andromeda will have grown until it occupies a considerable portion of the entire sky. Its light and its sweeping clouds of gas would dominate the heavens, so large and so close that it would begin to blot out the view of the universe beyond, the more distant galaxies hidden behind this great approaching wall of stars. It is worth being honest about what the Earth will be like by then. Long before this point, our own sun, going through its natural evolution as it ages, will have grown hotter and brighter, and the Earth will almost certainly have been rendered uninhabitable, its oceans boiled away, its surface scorched. Barring some extraordinary feat of engineering, by whatever intelligence might exist by then, there will be no one standing on Earth to look up. But perhaps, further out in the solar system, on some cold and distant world that manages to survive, something might endure to witness the sky filling with the light of an oncoming galaxy, a messy, asymmetric collision beginning to unfold across the heavens. Then, around 4 billion years from now, the two galaxies will truly meet. They will crash into one another, and their elegant spiral structures will be torn apart and fundamentally reshaped by the encounter. Vast clouds of gas will be scattered and compressed, and the orderly pinwheels of stars will be deformed into something chaotic and new. But here is a detail that often surprises people, and it is genuinely important to understand. Even though hundreds of billions of stars from each galaxy will be involved in this collision, it is statistically extremely unlikely that any two individual stars will actually strike one another. This seems impossible at first. How can two galaxies smash together without their stars colliding? The answer lies in just how empty a galaxy truly is. The space between the stars is so enormous, so vast compared to the size of the stars themselves, that the stars sail right past one another, like two swarms of gnats passing through each other across a great field, each insect missing all the others by an enormous margin. The galaxies will merge, but the stars will, almost all of them, simply glide past, untouched. That said, the stars will not be entirely undisturbed. While direct collisions will be vanishingly rare, stars will frequently pass close enough to one another to wreak havoc on each other's gravity. The delicate, finely balanced orbits of planetary systems, painstakingly arranged over billions of years, can be thrown into chaos by a passing star, their planets flung into new orbits or hurled away entirely. And our own solar system, if it still holds together in any recognizable form, will face an uncertain fate during all of this. Astronomers have run many simulations to try to determine where the Sun will end up after the Great Merger, and there is no clear consensus because the outcome depends on the precise, almost unknowable details of the Sun's position at the critical moments. In some scenarios, the solar system is flung far outward, perhaps cast into the outer reaches of what was once Andromeda, or even hurled clean out into intergalactic space, to drift alone in the void, one of those lonely, banished systems we spoke of earlier. In other scenarios, the Sun is thrown inward instead, drawn toward the turbulent, crowded heart of the new combined galaxy, where it might come dangerously close to the central black holes and be torn apart. We simply do not know which fates awaits our solar system. It hangs, for now, on the unwritten gravitational mathematics of a collision 4 billion years away. The collision itself is not a single event, but a long, drawn-out process. After the first dramatic impact, the two galaxies will not simply stop. Their immense momentum will carry them apart again, and then gravity will draw them back, and they will pass through one another once more, and again, and again. With each pass, the galaxies lose a little energy, swinging closer together each time, like two dancers spiraling slowly inward. With every one of these passes, hundreds of billions of stars are rippled and disturbed by the gravitational chaos, sent cascading in all directions, the once neat structures dissolving into great streams and shells of scattered suns. Over hundreds of millions of years, pass by pass, the two galaxies will gradually settle and merge toward a common center until they are no longer two galaxies at all, but one. The final and perhaps most dramatic stage of this merger comes when the very hearts of the two galaxies combine, when their central black holes meet. Remember that each galaxy carries a supermassive black hole at its core, Andromeda's giant of more than 100 million solar masses, and our own Sagittarius A star, more modest at around 4 million. As the merger proceeds, around 7 billion years from now, these two black holes will be brought together near the center of the new combined galaxy. They will not collide instantly. Instead, they will begin to orbit one another, circling round and round in a slow gravitational waltz. And as they orbit, they will fling away any stars that stray too close, using the energy of those encounters to gradually tighten their own orbit, sinking ever closer to one another over millions of years. Eventually, the two black holes will spiral down until they are within about a single light year of each other. And at this point, something profound begins to happen. Two such massive objects, whirling around one another at tremendous speed, begin to stir the very fabric of space-time itself, sending out ripples called gravitational waves. These are not waves in any material, not in gas or dust, but waves in the structure of space and time, spreading outward at the speed of light. They carry energy away from the orbiting black holes, and as that energy drains away, the black holes spiral closer still, faster and faster, the waves growing more intense. The gravitational ripples generated by this final dance would be felt across billions of light years of space, a tremor in the cosmos announcing the union of two galactic hearts. And then, at last, the two black holes merge. They become one, a single new supermassive black hole, binding the center of the new galaxy. Its mass, the combined weight of both its parents and everything they have devoured. With this final union, the long process of merging is essentially complete. Where once there were two great spiral galaxies, the Milky Way and Andromeda, turning separately in the dark, there will now be a single, enormous elliptical galaxy, a vast, smooth, featureless cloud of stars without the elegant arms of its parents. This new galaxy even has a name, a slightly whimsical one that astronomers have given to the future child of our two galaxies. They call it Milkomeda, a blending of Milky Way and Andromeda, a name for a galaxy that does not yet exist, but someday will. Collisions and mergers like this one, it turns out, are not rare or unusual events in the universe. They are commonplace, a fundamental part of how galaxies grow and evolve. Over the long history of the cosmos, galaxies have repeatedly crashed into and merged with one another, and these violent unions have played a crucial role in building the rich, diverse galaxies we see today, including the kinds of galaxies, like our own, that are capable of hosting worlds where life can take hold. In a strange way, the same violence that will eventually consume the Milky Way is also part of the process that made it the kind of place where we could come to exist in the first place. Destruction and creation, in the cosmos, are very often the same thing wearing different faces. But this great cycle of collisions and mergers has a limit. It cannot go on forever. Once the new elliptical galaxy, Milkomeda, has fully taken shape, it will not change its fundamental form very much from then on. The great structural drama will be over. What remains will be a slower, quieter process of consumption. Milkomeda will gradually absorb the rest of its companions, the remaining satellite galaxies of the local group, drawing them in one by one over billions of years. This includes the Triangulum galaxy we visited earlier, with its 40 billion stars, which will likely orbit the new galaxy for a long time before eventually being swallowed in its turn. But this process is slow almost beyond comprehension. It will take more than 150 billion years before the last members of the local group have finally been consumed by this monster galaxy. 150 billion years. The universe itself is currently only around 14 billion years old. The full consummation of our local group lies more than 10 times the present age of the universe into the future. But once it is done, that will be it. The local group will have become a single galaxy, complete and alone, forever. And here we begin to move into the deep future, into a story that grows quieter and dimmer and stranger the further forward we look. Because long before that final consumption is complete, something else will have happened. The gas that galaxies use to form new stars, the raw material from which suns are born, will begin to run out. Both Andromeda and the Milky Way will have spent much of their star-forming gas over their long lives, and by the time Milkomeda fully takes shape, there will be relatively little left for it to make new stars from. The merger will trigger one last burst of star formation, a phase astronomers call a starburst, when the compression and chaos of the collision squeezes the remaining gas and lights up a final generation of new suns. But this burst will be brief, and it will be less fruitful than the great bursts of star formation we have seen in other galaxies, because the fuel is nearly spent. It will be a last flowering, a final blaze of creation, before a long twilight begins, with no significant new stars being born to replace the old ones. The general population of Milkomeda will simply grow older and older. Stars do not live forever. Over enormous spans of time, an ever-increasing share of the galaxy's stars will reach the end of their lives, swelling into red giants in their final phase, and then either exploding in violent death or quietly collapsing into the small, dense, slowly cooling embers we call white dwarfs. The galaxy will be populated more and more by these dying and dead stars, and less by bright young ones. The light of the galaxy will begin, ever so gradually, to fade. And as all of this unfolds, the wider universe will be changing too, in a way that deepens the loneliness of the picture. Remember that the expansion of the universe is carrying galaxies apart from one another, and that expansion is not staying steady, it is speeding up. As the eons pass, this accelerating expansion will push all the galaxies beyond our local group, farther and farther away, faster and faster, until eventually they recede beyond any possibility of our reaching them, and finally, beyond any possibility of our even seeing them at all. Their light, stretched and dimmed by the ever-growing distance, will fade from view. There will come a time when an astronomer in Milky, looking out into the cosmos, would see nothing but their own galaxy, alone in an apparently empty void, with no other galaxy visible anywhere in the sky. The rich, galaxy-filled universe that Hubble revealed to us, that vast cosmos of countless island universes, will have effectively vanished from sight. We will never encounter, or even see, another large galaxy again. All that will remain within reach will be a few small, dwarf companions, the last scraps of the local group, offering only minor mergers, only the smallest morsels of fresh material, and these will not be enough. Without any meaningful source of fresh gas, without large galaxies to merge with, without the great rivers of raw material that once fed the making of stars, Milky will run out of ways to renew itself. It will have exhausted its mechanisms of rejuvenation, the processes that for so long kept it young and bright and full of new light. And so the galaxy will begin, slowly and quietly, to stagnate, to wind down, to die. This is not a sudden death, not a dramatic collapse or explosion. It is the gentlest and slowest of endings, playing out over timescales that strain the imagination past its breaking point. It will happen over tens of quadrillions of years. A quadrillion is 1,000 trillion, and we are speaking of tens of those, a stretch of time so vast that the entire current age of the universe is less than a rounding error within it. Across these unimaginable spans, the stars of the galaxy will continue to age and to cool. One by one, over the eons, they will exhaust their fuel and dim, and the dead embers they leave behind, the white dwarfs and the other cooling remnants, will slowly radiate away, the last of their heat, into the surrounding dark. There is a particular endpoint to this cooling that is worth dwelling on, because it is the final note of the entire symphony. Eventually, the stellar remnants will cool all the way down to a temperature of just 5 degrees above absolute zero, 5 Kelvin, almost as cold as anything can possibly be. At that temperature, they will no longer be hot enough to glow with any meaningful light at all. They will cease to shine, and the matter within them will, in effect, freeze solid, locking away forever the precious elements they once forged in their cores, the carbon and oxygen and iron that might, in a younger universe, have gone on to become new stars, new worlds, perhaps even new life. All of it sealed away inside cold, dark, impenetrable spheres of frozen matter, drifting silently through a galaxy that no longer makes light. And so, bit by bit, star by star, over a span of time we cannot truly comprehend, the galaxy will grow darker and dimmer. The bright spiral arms are long gone by now, replaced first by the smooth glow of an elliptical galaxy, and then by an ever fainter scattering of cooling embers. The light recedes, retreating into the dark like a tide going out and never coming back. And then, at the very end of this longest of all stories, the last star will finally fade. Somewhere in that immense darkness, the final glowing ember will cool below the threshold of light and wink out, and there will be no more. The the story of Andromeda and the Milky Way, the story of these two great galaxies that danced and merged and lived together for hundreds of billions of years, will at last be over. The galaxy will fall dark and silent, a vast cold graveyard of frozen stars, drifting through an empty universe with no other galaxy anywhere in sight. It is a sobering vision, I know. There is something almost overwhelming about following the story all the way to its conclusion, watching the lights go out one by one across spans of time that make a human lifetime, make the whole of human history, make the entire age of our species seem like the briefest flicker, and it would be easy to come away from this feeling small, or sad, or insignificant. But I would gently ask you to consider the other side of it, because I think the other side is far more important and far more beautiful. Here is the thing that I find genuinely consoling and even joyful when I sit with this immense story. We were born in the middle of it. Think about the full arc of what we have traveled through tonight. There was the chaotic, violent beginning, billions of years in the deep past, when galaxies were forming and crashing and devouring one another in the young, turbulent universe. And there is the cold, dark, silent ending, an unimaginable distance into the future, when the last star fades and the lights go out forever. And here we are, you and I, alive in the great bright middle of it all. We exist in the era of starlight, in the long, luminous afternoon of the cosmos, when galaxies are full of brilliant suns, when new stars are still being born in glowing clusters, when there are worlds with oceans and skies and the conditions for life. We arrived long after the chaos of the opening and unimaginably long before the darkness of the end. Out of all the possible moments in the entire history of the universe, we get to be conscious during the part where the lights are on. And there is something even more intimate than that, something I want you to carry with you. The violent history we have traced, all those collisions and mergers, all that consuming of galaxies and forging of elements in the hearts of stars, is not separate from you. It is the very reason you exist. Every heavy element in your body, the calcium in your bones, the iron in your blood, the carbon that forms the structure of every cell, was created inside a star, in the searing furnace of a stellar core, or in the explosion of a dying sun, long before the Earth was born. The same kinds of processes happening right now across Andromeda, the birth and death of stars, the scattering of their elements, the slow recycling of matter into new generations, are the processes that made the atoms you are made of. When you look at Andromeda, you are not looking at something alien and far removed from yourself. You are looking at a vast version of the very machinery that built you. You are, in the most literal sense, made of the same stuff, forged in the same kind of fire. I find it remarkable, too, how recently we came to understand all of this. Step back from the deep future for a moment and consider the deep past of our own knowledge. For more than 1,000 years, from Al-Sufi noting his little cloud in the year 964, all the way through the era of Marius and Messier and Herschel and Parsons, that faint oval of light was a mystery, misunderstood, assumed to be a nearby cloud of gas. It was only in 1924, when Hubble timed those pulsing Cepheid stars and measured the true distance, that we finally understood what Andromeda actually is. That means it has been only around 100 years, a single human lifetime, give or take, since our species first grasped that Andromeda is another galaxy and that the universe is filled with billions more like it. 100 years. Your own grandparents, or their parents, were alive in a world that did not yet know there were other galaxies. The entire modern picture of the cosmos, the picture we have explored together tonight, is astonishingly young. Think of all the people in this story, doing their honest best across the centuries. Al-Sufi, looking up over 1,000 years ago and bothering to write down a faint smear of light. Herschel, peering through his telescope and making a careful, brilliant observation that led him to a conclusion that turned out to be wrong by a factor of more than 100, and yet was entirely reasonable given what he knew. Curtis, recognizing the meaning of those faint novae and bravely reviving an idea that most of his colleagues found impossible to accept. Shapley, arguing with conviction and genuine intelligence for a smaller, simpler universe, and being wrong, but being wrong in a thoroughly understandable way. Hubble, finally settling the great question with patience and a magnificent telescope and the quiet rhythm of pulsing stars. None of them could have imagined how deeply Andromeda's story is bound up with our own. None of them could have known that the faint cloud they puzzled over is not merely a distant neighbor, but our galaxy's future partner, the galaxy with which the Milky Way will someday merge to become something new. They were reading the opening pages of a book whose later chapters we are still only beginning to understand. And that, perhaps, is the most hopeful thought of all. Because if we have learned this much in a single century, if we have gone from believing the Milky Way was the entire universe to mapping the structure of a galaxy 2.5 million light-years away, to glimpsing the gravitational shadow of a planet in its midst, to charting the collision that will reshape our skies 4 billion years from now, then imagine what those who come after us will learn. Imagine the knowledge our descendants will hold a century from now, or 1,000 years from now. Imagine the instruments they will build, the questions they will answer, the mysteries we cannot even formulate yet, that they will solve as easily as we now read the distance to a star. The story of our understanding of Andromeda is not finished. It has barely begun. We are still, in a sense, standing where Al-Sufi stood, looking up at a faint patch of light, except that now we know just enough to understand how much we do not yet know. So let me bring you back, at the end of all this, from the deep future and the deep past, from the frozen stars and the merging black holes and the great cosmic spans of time, back to something simple and close and entirely within your reach, back to a clear, dark night, in autumn or winter, away from the lights of the town. If you go outside on such a night and let your eyes adjust to the darkness and look toward the constellation of Andromeda, you can find it. That same faint oval that Al-Sufi described more than 1,000 years ago. That same smudge that Herschel misjudged and Hubble finally measured. It will look like almost nothing, a soft, pale blur, easy to overlook, easy to mistake for a trick of the eye. But now you know what you are looking at. You know that it is not a cloud and not a flaw in your vision, but an entire galaxy, more than 1 trillion suns, larger than our own, turning slowly in the dark. You know that the light entering your eye in that moment left Andromeda more than 2 million years ago, and has been traveling, unbroken and undisturbed, across the vast emptiness between galaxies, just to arrive at you, on that particular night, in that particular glance upward. You know that hidden within that faint glow are star-forming clouds blazing with young blue suns, hundreds of globular clusters, the swallowed cores of vanished galaxies, the shadows of unseen planets, and a monstrous black hole 100 million times the mass of our sun. And you know that it is coming toward us, slowly and inexorably, on a journey of its own that will end, billions of years from now, in a union that will give birth to a new galaxy neither of us will ever see. There is a particular kind of quiet that comes over you when you look at something like that, and truly understand it. The faint light no longer seems faint. It seems, instead, almost overwhelming, charged with meaning, a single visible thread connecting you directly to the deep structure of the universe. You are a small, warm, living thing, standing on the surface of one small world, looking across 2.5 million light-years of darkness at the nearest of the great galaxies, and somehow, against all odds, understanding what you see. That capacity to understand, to look up at a smudge of light and trace it back through history and forward through time, to know its size and its distance and its fate, is one of the strangest and most precious things our species has ever managed to do. So the next time you find yourself outside on a clear, dark night, take a moment, let your eyes adjust, find that faint oval in the autumn sky, and simply look at it for a while, knowing everything you now know. There is no need to do anything else, no need to reach for it or understand anything new. Just let yourself feel the quiet wonder of it, the vastness held within that small, soft glow, the long story of which it is a part, and of which you, too, in your own brief and luminous moment, are a part. The light has traveled 2 million years to meet your eye. The least we can do, now and then, is to look up, and to marvel, and to be grateful that we are here, in the bright middle of the story, awake and aware, beneath the turning sky.